Welcome back to Everybody Codes 2025. Today we have a pretty interesting problem. It's not too difficult to implement actually, but it's still interesting to think about. So today we have a bunch of gears that we're working with, and for the first part we're given a list of gears that are all put together in sequence, and the number of teeth is given to us per gear line by line like this. So they have an animated example for us, which is pretty cool. So looking at our sample, the first gear has 10 teeth and the second gear has 7 teeth. What that means is that the first gear turns at a rate of 7/10 of the speed of the second gear. Essentially, the reason that makes sense is because the teeth lock together like this, so the number of teeth moving past this point has to be the same for both gears on either side of the intersection. And so because the left one has 10 over 7 times more gears than the right side, the right one is spinning 10 over 7 times faster than the left side. And so if we look at this example, this gear, every time it makes 7 full rotations, this one makes 10 full rotations, and so on and so forth. And so as an example given to us, where the first gear has 128 teeth and the second gear has 64 teeth, we see that every time the first one makes a full rotation, the second one makes 2 full rotations. And then every time the 64 gear turns once, the 32 gear turns twice, and so on and so forth. And so if you take all of these ratios, you'll get a total ratio of 16. Now, one thing to note here that makes this problem a lot easier to solve is that the middle numbers are completely irrelevant. This is because when you chain gears together, the overall turn ratio just depends on the ratio between the first gear and the last gear. The reason this makes sense is because the ratio of 128 to 64 times the ratio of 64 to 32 is the same thing as the ratio of 128 to 32 because you can just cancel out the 64 on both sides. So what we're essentially doing is taking 128 divided by 64 and multiplying that by 64 divided by 32. And so because one side has 64 on the bottom and one side has 64 on the top, we can just cancel them out entirely and get a total ratio of 128 over 32. And we can continue this cancellation until we just get a ratio of first number divided by last number. So that's really all that this question is asking. We turn the first gear 2025 full rotations, and we want to know how many times the last gear turns fully. And so we just take the first number and divide it by the last number. And so in order to grab the input, what I always like to do is use open0. That's a trick I've been using for many years in Advent of Code. It opens the standard input as a file, which allows you to use .read to just grab the entire input. You can also import sys and do sys.standardin.read. That works just as well, but open0 is faster to write. Once you read the entire thing, you can split it on lines. And so that will give you a list of each line of input. So if we run this code on this input, for example, we get each of our lines. And so in order to get the first and last value, we can do x equals int of the first line and y equals int of the last line. You can do this if you want. What that's essentially doing is it's saying that we want to unpack the list of lines into this assignment where x is the first item, y is the last item, and the underscore is a list containing all of the intermediate items. The star notation here is a spread operator. What it does is it makes this a variable length operator, or variable length value, which is a list that holds all of the remaining values. So we could also do like x, y, star, underscore z to make x the first, y the second, z the last, and the underscore everything in between. You can do that as well. I don't find it to be any clearer though. So this is the method I'm going to stick with. And then we just want to see what happens when you take the ratio of the gears and multiply it by 2025 full rotations. And then, because it's asking for full turns, we can floor the value just to make it easier to copy paste. So we can just cast that to an integer, which will truncate off the value. And so that'll give us 15888. And running that on our actual input, that'll give us our answer of 20,876. Looking at part 2, fairly straightforward still. We are now asked to determine the minimum number of full turns of the first gear in order to turn the last one at least this many times. And so we're basically inverting the ratio here. First time we're asking if we turn X this many times, how many times have we turned Y? Now we're asking if we turn Y this many times, how many times does that turn X? Since it's asking for the minimum number of turns for the first gear, this time we're not flooring the value. Because in this example, if we turned this one fewer time, we'd get just below this value. Whereas with this number of full turns, we go above this value. But because we need to turn the final gear at least this many times, then we need to round up the number of times we turn the first gear. And so input is exactly the same, but this time we're going to take this value, multiply it by y, and divide it by x. And so, looking at this example, this gives us a value telling us that we need to turn it a bit over this many times and a half. But because we need to turn the last gear at least this many times, we need to round this value up. And so the way you can round up is using math.ceil, standing for ceiling, which rounds a value up. And that will work for the output. You can also do this. So what this is doing is, since int, I stand corrected, you actually can't do that because, yeah, int is the one that truncates towards 0. So, never mind, you actually cannot do that. So yeah, just use math.ceiling for purposes like this. And so trying this on our actual input, we get our answer of big number. Finally, looking at part 3, we now have a bit more complex of a situation. This time we do actually have to look at the middle values. So it's common when you're doing gear change to have something like this where you'll have two gears of different sizes attached to one axis. And so what this does is it makes the two gears turn at the same ratio. So looking at this example, we turn this gear with 10 teeth against this gear with 7 teeth, which means that they still have the same 10:7 ratio of speeds. And then we attach this 7 gear to a 14 gear on one axis, meaning they spin at the same rate. And then we turn this 14 gear against this 8 gear, which turns at a 14:8 ratio. And then we attach the 8 gear to a 16 gear, which turns against the 6 gear to rotate at a 16:6 ratio. So this is a very good way to speed up gears, because recall that with this example, the middle gears didn't matter, which means that you're basically just turning one gear against another gear, which means that the ratio you can achieve depends solely on how many teeth they have. So if you want a 1 to 1,000 ratio, you need something comical like this gear having 5 teeth and this one would need 5,000 teeth. With this one, what we're doing is we're multiplying all of the ratios together. So the first two gears have a 10:7 ratio, and then these gears have a 14:8 ratio, and then these gears have a 16:6 ratio, which means that we can spin this gear a lot more slowly than this gear. And if we wanted a 1,000-to-1 rotation ratio, for example, we could just do 3 10-to-1s in a row or something similar to that. And so in practice, this does get used if you want to have larger gear ratios. More commonly, what you'll see is if you want to convert a faster motor into more power but slower, you can power this gear quickly to turn this gear slowly but with a lot more force behind it. Or I guess torque, sorry. So to take the input, what I found to make the most sense was to read the entire input as one string again, and then split it using the pipe. So if we use this example here, we can take the input as an entire string and then split it on the pipe, which means that we get a list of strings that contain a new line in between. So this tells us we have 3 gear ratios to consider. The first ratio is 5:5, the second ratio is 10:10, and the third ratio is 20:5. And so what we can do is we can take each one and split it on new lines. And so that'll give us a list of pairs which represent our ratio, which is a bit easier to work with. What you can also do here is map string.splitLines over this input. That works as well, and the reason this works is because calling .splitLines on a string is the exact same as doing string.splitLines on that string in Python. These two are exactly identical. In fact, calling a member function like this actually behind the scenes just calls the same member function on the class, but with the object as the first argument. But we won't get into that in this video. For now, I'm just going to use the first one because I think it's a bit clearer what it's doing. And then we basically just need to take the product of all of the ratios. So we can set a total ratio, which is initially just going to be 1 because when we're taking a product, we need to start at 1. And then we can say for x, y in ratios, this will go through each of the gear ratios, so 5, 10, 10, and 25. And then we can just say total times equals the ratio between these two gears. And the ratio will just be x divided by y. And so at the end, we want to know how many times the last gear turns when the first gear turns 100 times. So we multiply this turn count ratio by 100, and then it wants to know the floor of that value again. And so that gives us our answer for part 3. So not too complicated of a problem to actually implement. You'll see that the code is actually quite short, and part of the reason it's not like a one-liner is because I wanted to make it a bit more clear what's going on. Because realistically what you could do is you could just do this, but I wanted to make it a bit more clear what the solution is actually doing. So, interesting problem. I like this kind of problem because it's not too complicated to actually write out the code, but it more so involves reading the problem and understanding the nature of the problem to see that because you're chaining ratios together, the middle values all cancel out, and so they don't matter, so you can get a pretty fast solution time. And then the last one is a bit more interesting, but honestly arguably more straightforward because it doesn't require you to make the ratio cancellation connection because there is none to be had. So not too difficult of a problem, still looking relatively easy for a day 4, but looking forward to seeing what will come next, and maybe the difficulty will start ramping up a bit more aggressively next week. In any case, that's all for this video. Thank you for watching, and I'll see you tomorrow.